The black tufted capuchins integrate contextual factors from their environment into the meaning of their signals. It's a question of perhaps the evolution of pragmatics in language, the importance of the context, both cultural and environmental, in the meaning of a particular word, a symbol, or it could be an indexical signal as well. Well, a way of predicting the presence of this contextual pragmatics in a primate is possibly modelling it using a neural network to make some predictions of how your primate should behave if these pragmatics are in place. And that's exactly what I've tried to do here with black tufted capuchins, Sapajus nigritus, in particular a group from Iguazu National Park in Argentina. So what we've got here is Capuchi-Net. What we're looking at here is one of the final output systems here. So you notice these lines going across here are actually axons that are projecting from the visual system, and there will be a separate part, a separate video which I will address the visual system for Capuchi-Net. But at the moment we've got the auditory system up here which receives signals, the semantic system, and we've got a decision module, and we've got an output motor module. So to begin with, I'm going to talk about the auditory module. This curl here, it's a figure of 9, is a symbolic representation of the cochlea, which is just behind the membrane of your eardrum. And what the cochlea does is, as it spirals in, it gets more and more constricted. And what this enables your ear to do is to take multiple frequencies from a sound wave in your environment. And when the sound wave hits your ear, this separates the sound wave into all the component frequencies that make up the sound wave. So, and because it constricts, it goes from low frequencies as it goes in towards higher frequencies. And so each of these circles is a neuron which fires for that particular frequency within the cochlea. And this in turn projects to the primary auditory cortex, which is what these 7 neurons here are modelling. And because each of these neurons are connected to their respective place in the cochlea, they are also representing low to high frequencies. In particular, this is 0.5 kilohertz. This is 100 kilohertz. This is 200 kilohertz. This is 400 kilohertz. This is 800 kilohertz, 1600 kilohertz, and then 3200 kilohertz, which is the uppermost limit in at least marmoset auditory systems. I know of no current research into the auditory cortex of black tufted capuchins as of yet. And these then outputs to these 2 neurons here, which are higher order association auditory neurons. So capuchins have two essential predator alarm calls. One which is a bark, which is a single sound unit, which is around about 400 to 600 kilohertz within that range, and it's a solitary one. So the bark neuron, which will detect when a bark spin is present in the auditory field, is sensitive to just one of these neurons. Then you've got a hiccup receptive neuron. This is the second alarm call in black tufted capuchins, which comprises of a hic, which is a high frequency sound. It sounds to be around about 600 kilohertz, and a cup, which is a second unit and is a lower frequency, I'd say around about 100 to 200 kilohertz. So this neuron is sensitive only when it receives a high frequency, and then it remembers that higher frequency long enough for the lower frequency to hit it, which is reflected in the weights between the connections. Now, the bark call in Capuchins elicits what we believe to be a representation for a raptor or a bird of prey like an eagle. And this connection is here. This is the neuron that represents a raptor. The reason why a single neuron can represent raptor is to do with the visual system, which is on further along the network on the left here, and it receives connections from the visual system which represents a schema for raptor, which is why this neuron can represent raptor. So raptor has been sensitized to the bark call, such that if the bark call is heard, the raptor representation is activated. Now, this is a functionally referenced signal in black tufted capuchins, meaning that bark only refers to raptor. A bit like laughter, responding, if you heard someone laughing, you'd interpret it that someone was happy or found something funny. Now, the hiccup alarm call is a bit more complicated in that it doesn't stand unitarily for one thing in the environment. If a hiccup is interpreted by a receiver, it can interpret it, one, as a felid, like a puma or a jaguar in the rainforest, a large cat, and that elicits an escape response. But it's also used in situations where a snake is present. So you can see it's a general terrestrial predator alarm call. And so the hiccup activates both of these neurons, one for felid, one for snake, and yet again they're connected to the visual system to make sure that this neuron represents felid and this one represents snake. Another aspect is that Capuchins will make this alarm call when they're receiving agonistic interaction or have received injury from another Capuchin in a fight. And so the hiccup alarm call also, to some quarters, activates the representation for Capuchin. This neuron here, because this is the semantic system, which is roughly in the inferior, medial-inferior temporal lobe, it also has a platform neuron. This is a neuron that's sensitive to the presence of a feeding platform. This is because primatologists have been studying the behaviour of Capuchins at feeding platforms, which kind of simulates food contest when there's a clumped amount of food, in this case bananas, and the Capuchins quite often might compete over the food there. Now, for the predator alarm calls, once these predator neurons are activated, they feed forward and project towards the posterior cingulate cortex, which is what this area is meant to represent. The posterior cingulate cortex is just superior to this region if we were looking at the actual Capuchin brain. This is not to say that this neural network actually is meant to be a Capuchin brain. Rather, it's just meant to mimic the processing that might be possibly going on in Capuchin cognition. But this area is a motivational area. If the animal's emotional state changes, it will feed forward to the prefrontal cortex, which is an area at the front of the brain, the higher order association cortex, which will in turn make a decision. So this could be called the decision module. Given a predator, what is our decision? If this neuron is activated by a predator and the primate goes into an aroused state, the black tufted capuchin gets worried that there's a predator possibly in the area, it will likely make the black tufted capuchin want to run away from the predator. And so the posterior cingulate cortex here is projecting to the motor cortex. And in particular, it activates neurons for the left front limb, the right hind limb, which in turn then activates the left hind limb and right front limb, and this is to represent, well, these would synapse with efferent muscle connections to create a quadrupedal sequence gait to make the primate run away from the predator. Another aspect I've added to this neural network is that it activates a visual scanning thing, so that in future models, the primate, when it's not got away from the danger, it can then inhibit the runaway of response, but that can be ignored for now. So essentially, what you'd expect is if a predator alarm call, like raptor alarm call, in this case the bark, is activated, raptor representation is activated, it panics the primate, the black-tufted capuchin, and it elicits an escape response here, which is what we're seeing in the neural network here. So I'm now going to reset the dynamics to halt that processing. And same with hiccup, we'd expect it to activate the felid representation, the snake representation, and down here the capuchin representation, because after all, the capuchin is the animal that's making the alarm call, and that's all the possible meanings that this signal could mean. And then it should activate a predator escape response. And so, as you can see there, cochlea, auditory cortex, it activated the hiccup field, the predator field, and then elicited an escape response, as you would expect. However, capuchins are quite clever, and they've realised that in a feeding context, at the feeding platform, which is this neuron here, in these contexts, they can make a fake alarm call to make other capuchin monkeys run away, so that they can stuff their faces full of bananas and eat all the bananas without getting into a contest. And because this has been shown to occur primarily in the research of Wheeler in 2010, what has also been shown is that other capuchins that hear this alarm call within platform contexts are less likely to run away from a predator, because it is possible that they realise that it's just a false alarm call. What would this look like semantically? Well, it would be the case that in the presence of a platform, a feeding platform, this neuron here, this hiccup signal should not mean predator, it should mean that it is just a capuchin, which is this neuron here. This should just mean this and not this. And that's essentially what a counter-deceptive capuchin should be processing. If it takes the environmental context, like the feeding platform here, into account when considering the possible meanings of this signal. So, how do we now model this in the neural network? Well, I've set up an experiment here to test this neural network. Right now, I'm in my garden. Apologies for the hoodie, but it's winter. It's January right now. It's 5 degrees Celsius, and I'm pretty cold. But what I've done is I have set up a feeding platform as it would occur in a typical feeding experiment, if you will. Any experiment would use the feeding platform in the Iguazu National Park, which is you have a feeding platform down and you have banana pieces that are roughly around that thickness, about 1.5 to maybe around 2.5 centimetre slices of banana. And so I've used a palette and I've chopped up a banana. This is my garden. Unfortunately, I've got a cat. Well, not unfortunately, I love my cat, but she's just sitting on the feeding platform, but that's okay. She kind of looks like a black tufted capuchin, I guess. She can simulate another black tufted capuchin here. And so yeah, that's what the feeding platform looks like. So going back to the neural network, what I've done here is this platform neuron. What it usually does is it receives a connection from the visual system designed to recognize a feeding platform. But what I've done here is I've connected it directly up to my camera, and what this box does is it recognizes the shape of the feeding platform according to principles that are similar to the visual system of my network. So essentially, if you see a feeding platform in this lower white hemi part of the square, then it will activate the feeding platform, which, due to learning in the capuchin, inhibits the representation for felid and snake. How the primate has learned this and how my neural network has learned this is part of a different another film I'm going to be making on this neural network, in which there's a hippocampus system in the Capuchi-Net, but that'll be saved for a future occasion. So what I'm going to do is I'm going to shift around here and point the camera at the feeding platform. You can just about make the shape of the feeding platform there, that square right there. Just make sure it's got the camera's pointed at it correctly. It's not helping with my cat sitting on it. Right, that will do. So now if we play the hiccup alarm call, the only neuron that is activated is the capuchin. Which in turn is considered to be that it's just the capuchin. In this case, if we look at the camera here, my cat, the capuchin right there, that it's just a false alarm call given by a capuchin to deceive, and felid and snake aren't activated, and consequently the primate is not aroused into a state of anxiety, and the motor network isn't activated. See, no escape response. An interesting prediction that this neural network makes, in addition, is that because raptor is a functionally referenced signal, the bark signal, we're talking about bark, not hiccup anymore, because barks are never elicited in feeding platform contexts, there should be no link between feeding platform and raptor representation. And furthermore, because it's a functionally referenced signal, i.e. that bark only ever means raptor, it doesn't mean anything else as the hiccup does. It means that it should not take into account, or the primate does not need to take into account, contextual environmental factors in order to understand the signal. It should just be that if it hears a bark, it means it's a raptor in whatever context. But what we see here is that in a feeding platform, we're still in the feeding platform situation. There's the feeding platform, and it's still activating platform. If we play the bark alarm call, we see that the raptor representation is activated. And it still activates escape response. What does this neural network essentially mean? Well, this essentially means that if it is true that black tufted capuchins are taking into account contextual factors from the environment, i.e. what we're seeing immediately to the left of my finger here, the presence of a feeding platform, for example. If they're incorporating these environmental factors into the meaning of their signals, then for functionally referenced signals that don't require this meaning, there should be a different resultant strategy to the alarm call. There should be a different behavioural response between platform situations. So if we're correct that capuchins take into account the context of that they're in while they hear a signal, then essentially they will produce an escape response to a raptor call, to a bark, in both platform contexts and non-platform contexts. And that's essentially what this model predicts, is that capuchins, if you pay a bark call, they'll run away in both contexts. And that's that neural network. But what if capuchins aren't taking into account the meaning of their signal, the context and the meaning? If they can't do that, if they don't have any pragmatic cognitive prowess whatsoever, they haven't evolved that, it suggests that a slightly altered neural network, but this area here is going to change ever so slightly. So I'm going to reset the dynamics of this one. And we're going to load our second neural network. This one is pretty much the same: cochlear, auditory system, semantic system, decision module, and motor module. However, we've changed the connections. Here, the hiccup still means felid, snake, and capuchin, and bark still means raptor, but we've designed the network such that meaning is the meaning doesn't take into account the contextual factors. It's the decision that takes into account the contextual factors. So this could be the case if a capuchin was at a feeding platform and it hears a hiccup alarm call, but it's just too busy eating. In other words, it's too busy thinking about the feeding platform to really take into account that there's been an alarm call at all. It just ignores the alarm call because it's too busy eating, which is the same as the feeding platform inhibiting the arousal of the primate to make the escape response. In a feeding platform context, the primate never gets aroused into anxiety because it's too satisfied with the fact that it's got bananas. Context is only considered in decision and not in meaning. How do I predict this neural network will unveil given the signals? It predicts that there should be an escape. If it's not in a feeding platform context, which it's not, this neuron is not activated, we should still get the same escape responses as normal. That was a hiccup. Decision, it generates an escape response. Now we're going to look at the bark alarm call. Raptor, decision, escape response. Okay. But in a feeding platform context, what would we expect? Well, if the feeding platform inhibits the ability of the primate to get aroused, or the decision to activate an escape response, then we'd expect that it doesn't matter if it's a bark alarm call, meaning raptor, or a hiccup alarm call, the primate should never elicit an escape response. So I'm going to move us back over to the feeding platform, the mock feeding platform. See, the feeding platform neuron has been activated because there's a feeding platform in the visual field right over there. Now if we play the hiccup alarm call, and just as before in the previous network, there was no escape response. But this case is slightly different, because the reason for that isn't because of the meaning, it was because the arousal to escape has been inhibited by this feeding platform here. If we activate the raptor alarm call, remember previously the raptor alarm call, what it did was it still elicited an escape response despite being in the platform context, because it was being interpreted, because the meaning was fixed. But in this neural network, the primate isn't interpreting meaning, it's just making decisions based upon the context. Which means that given a raptor alarm call, now the predator, the primate should still not elicit an escape response. And that's what we see here. In this case, if this is true, that black tufted capuchins don't take into account contextual factors in their meaning, then given a raptor alarm call in a feeding context, they'll ignore it because they're too busy stuffing their faces full of food. I mean to a primate, these banana pieces are so packed with glucose. It's a very valuable resource. I mean, who can blame them for getting excited about a banana piece?